This video contains a pink hippo puppet, an example about hearing loss and zombies eating brains, mention of storing body parts in a fridge, and the Dalek of statistics. Some LEGO characters may have been harmed during the making of this video.
Welcome to the first lecture on this module. And today is the first of a series of 5 lectures, maybe 6, depending, who knows, that's going to look at the spine of statistics. So what is it that we mean by the spine of statistics? Well, basically, in psychology and other sciences, there's a kind of process that you go through that is common to sort of everyone, really. You start off with some kind of question that you want to answer, a scientific question that's been driving you mad, making you lose sleep. You're like, oh my God, I got to know the answer to this question. And what you do, if you're a scientist, I mean, you know, if you're a normal person, you just go on Google. But if you're a scientist, you try to collect some data to begin with. So the whole process starts off with something known as sampling. So you'll go and collect some data about the question that you're interested in. So that's the first part of the process. Once you've collected some data, you will then visualize the data. So you'd plot it in some meaningful way. We're not going to talk about that too much on this module, but you're going to rehearse it a lot in the interactive tutorials that you do. The big thing is that you'll then fit some kind of statistical model to the data, which tells you something meaningful. Now, normally there's 2 types of things that we're interested in when we fit a statistical model. The first one is estimation. So this is addressing the question of how big is the effect that I've looked at. So how big is the effect of this variable versus on this other variable? So you can do estimation in one of 2 ways. I mean, they're both complementary. It's not either or. In one of 2 ways. The first is you can have what's known as a point estimate. So this is a single value that kind of tells you, well, as this variable changes by 1, this other variable changes by 2, for example. So it's a single value that kind of quantifies the effect that one variable has on another. The other way you can do it is with something known as an interval estimate. So you may have heard of confidence intervals before. That's an example of an interval estimate. And that's where you're kind of saying, well, it's complicated what you might be saying, but we'll get into that. You're kind of saying the effect that this variable has on this other variable is somewhere between this value and this other value. So it's not a single value, it's like an interval within which you think the actual size of the effect is going to fall. So that's one thing you can do, estimation. The other thing scientists do an awful lot of, which we're going to cover in a couple of lectures' time, is hypothesis testing. So you can set up your model in such a way that it is testing a hypothesis that you're interested in. So this is more a kind of looking at an effect in a sort of dichotomous way, like does it exist versus does it not exist? And we'll get into whether this is a good idea or not in due course. But scientists do it a lot, so they basically test hypotheses. So when you fit a model, there's 2, I'd say complementary things you can do with that model. One is estimation, the other is hypothesis testing. Whenever you fit a model, you're assuming all sorts of things, and what you assume might depend on the model. But basically, for the model to be a kind of accurate representation of reality, certain things need to be true. So whenever you fit a model, what you should also be doing is assessing whether there's bias in that model. So again, we've got a lecture in a few weeks' time that talks all about bias, so how you assess the assumptions of the model or whether anything in the data might be biasing the model. And by bias, it could be biasing the estimation process. So it could bias the the values that you estimate in the model, but it could also bias the hypothesis testing part of the model. So it could bias the tests that you do on the model. So that's an important part of the process. And depending on the outcome of having a look at your assumptions, you might want to fit a variant of your original model. There's a whole kind of family of models known as robust models. So these are models that are, well, as the name suggests, robust to the violations of assumptions. So This process is kind of fairly constant. Whenever you are interested in any kind of scientific question, you start with a question, you would operationalize that question in some way, sampling, you'd collect some data. Once you've collected the data, you'd visualize it, fit a statistical model, and you can use that statistical model either to do a process of estimating the effect or effects, or you can use it to test hypotheses. And you would always then test the assumptions of the model, look for bias, trying to assess, is this model a reasonable representation of reality? And if the answer to that question is no, you fit a different model. And at least on this module, the different models that we're going to look at are a family of robust models. So throughout this module, I want you to have in mind this process, because after we spend about 5 or 6 lectures, I think, just going through the different parts of this process. And then after that, all we're really doing is repeating this process for slightly different models. So we'll have a look at that red blob in the middle that says fit model, and we're going to ask the question of, well, what kinds of different types of models can we fit? But in every case, for every model that we fit, sampling will be involved, estimation will be involved, we'll look at hypothesis testing, we'll look at assumptions, and we'll look at fitting robust versions of the test. So there's a lot of kind of commonalities throughout all the lectures. Now within that framework, there are, I think, 5 key concepts, which if you understand these 5 concepts, then I think you've gone a long way to understanding what's known as frequentist statistics. So you've gone a long way to understanding the type of statistical models that psychologists typically fit. Actually, not just psychologists. And the 5 concepts are the standard error, parameters, interval estimates, null hypothesis significance testing, and estimation. So our job in the first few lectures is to go through these key concepts, because if you have them in place, everything else to some extent, nothing's easy in statistics, but everything else to some extent will hopefully fall into place for you. So for today in particular, we're going to start off with just looking at the family of models that psychologists typically fit. So it's something known as the general linear model. Some of this may be familiar to you, but there's no harm in going over it again. So we're going to talk about what the general linear model is. We're also going to have a look at how, well, it has the name general, right? And there's a reason for that, which is it's kind of a model that can adapt to a variety of different situations. And we're going to look at how this particular model is a more useful way to think about psychological statistics than how it is often taught or often presented historically. We're also going to have a look at the estimation process. So how is it when we fit a model, we estimate parts of it? So that's the basic précis for today. So your learning outcomes. Hopefully you're going to understand that most of psychological statistics has a lot of commonalities to it. So you only really need to learn one model and one process, and that model and process applies to any situation. All that changes is the exact form of the model, but everything else around it stays the same. We'll have a look, like I said, at the linear model. So what it is mathematically, but not in too much depth, what it looks like visually, and like I said, how other models that might be familiar to you or you might come across in your scientific reading are actually just variants of this one model. We are going to have a look at what model parameters represent. So these are known as betas. We're going to have a look at what they represent, and we're going to have a very brief look as a kind of precursor to another lecture as to why we use sampling. And hopefully that's what you're going to get out of the next 45 minutes or so. Oh, and I forgot about this one. And understand least squares estimation as well. Maybe. So I've been teaching statistics a long time, and I teach it to psychologists, and often they are not, it's not their favourite subject, let's put it that way. It's fair to say, it's not their favourite subject. So I often ask myself, because I love statistics. I mean, I was about to say I don't love it like my children, but I do love statistics. And so it's, I do puzzle over why some students hate it so much. One of the things I think that scares people off of statistics is it can sound very complicated, and people, there's lots of kind of jargony words, and you've got to kind of get your head around them. People talk and, they're saying words like parameters and, we'll come across this later, heteroskedasticity and things like that. And it's like, oh, what are the long words? What do they mean? So it's kind of very bewildering, and you're also, people like thrust equations at you, and they all look different, and you're told that they all do different things, and they've all got Greek symbols in, and it's all a bit kind of weird and bewildering. But actually, there's a kind of a set of key concepts, and if you understand those key concepts, a lot of the peripheral stuff you can kind of get away with not knowing to some extent. Or at least get to know it when you've got the foundations in place. So the question is, can we make statistics a bit less like this? And I think the answer is yes, we can, by focusing everything on this general linear model, which is a framework that kind of encompasses, as I keep saying, most of the models that are fit in psychological statistics. So what is the general linear model? Essentially, it boils down to one equation. In its simplest form, all we're ever doing is predicting an outcome, so something we've measured, a variable that we've measured, and we're predicting it from a model. And that model, as we will see over the course of this module, can kind of expand and contract. But just think of it as a model, though, and worry about the specifics of the model in specific cases. But we're just predicting it from a model, and there'll be some error in prediction. So, for example, you might want to predict aggression from use of video games. That's an example of some psychological research. So the outcome you're trying to predict is aggression. So you would measure that in some meaningful way. And the model you're trying to predict it from includes a variable that looks at video game use. But it could have lots and lots of other variables in there as well. But there'll always be error in prediction. So if you take a particular kind of, if you want to say, well, if you play video games for 7 hours a week, this is how aggressive you are going to be, there'll be error in that prediction. So we always have to bear in mind these models are never perfectly predicting what goes on. There's always uncertainty in prediction. There's always error attached to it. So essentially, we're predicting an outcome, and the little hat there on the outcome is telling us that it's a kind of an estimated value or predicted value. And we are predicting it from some variable or variables that we've measured that we call predictors. And each predictor has what's known as a parameter, so a beta value. So let's do a quick zombie quiz. Now, if you were to walk around campus, you will notice that zombies walk among us. Most of them in the maths and physics department, to be fair, but they're around, believe me. Now, I was interested in whether there were different food habits for the zombie faculty versus the human faculty. So what I did was I sat out in some of the canteens around campus, and I took notes of whether people coming in, when they chose their food, whether they chose to have potato chips with their food, or whether they chose to have brain chips, because we all know zombies like to eat brains. So a researcher, me, I counted how many humans and zombies chose brain chips or potato chips to accompany their dinner at the university canteen. Now, I've been here a long time, so I'm well versed at accurately predicting whether someone is a zombie or a human. So I can categorize faculty members as human or zombie. So we can assume that's correct. And then I just took a note. just hung out in the canteen all day with my notepad. If they chose brain chips, I ticked brain chips. If they chose potato chips, I ticked potato chips. Here's my data. So I've essentially got a contingency table, and within it, I've got some humans and I've got some zombies. And I've got a record of how many humans ate brain chips, 28 of them did, and how many humans ate potato chips, 42. So in the humans, more ate potato chips than brain chips. And for the zombies, I have the same data. So 61 of them ate brain chips or chose brain chips, and 57 chose potato chips, so similar amounts. My question is, how do I analyze these data if I want to test the hypothesis that zombies eat more brain chips than humans? So mentally, you can now do that little quiz in your head and see what answer you come up with. Now, probably, if you look at kind of, a lot of textbooks and stuff, probably my own ones included, you'll find that they tell you to do a chi-square test. So if you've got categorical data, these are categorical data. We've got categories of zombies and humans and categories of brain chip and potato chip. So everything's categorical. We've just got count data. We've just counted how many people fall into the combinations of categories. Everything will tell you count data, chi-square test. That's the law. And if you deviate from that model, literally hell will break loose. Beelzebub will come from Hades up to Earth and destroy us all. Or worse than that, the Dalek of statistics will materialize. Now, because obviously some people at the start of statistics modules get very freaked out, and I don't want to freak you out anymore, but there is something known as the Dalek of statistics. And the Dalek of statistics, it was a renegade Dalek, and basically they needed a job for it to do. So they set the Dalek of statistics a job of policing the models that people fit to their data. So if you fit the wrong model, the Dalek of statistics materializes and tries to exterminate you, and quite possibly exterminates everyone else on the planet. So, high stakes. But it's okay, because we know if we have categorical data, we do a chi-square test. Now, what I want you to note here, just for now, obviously this is not the be all and end all of everything, but note this is the p-value associated with the test applied to these data. So it's 0.121 rounded off. So 0.121, that's the p-value. So for lots of scientists, that would be the thing that they interpret. So the thinking is, I'm in a bit of a rebellious mood today. So I feel like seeing what happens if we do something else. Let's just try something else. Let's just flout the laws of statistics and try something else. And what we're going to try is a Spearman correlation. I'm going to try this because, well, a Spearman correlation is something known as a non-parametric test, which everyone seems to think means that it makes no assumptions, but it does make some. So a Spearman correlation, but it looks for associations or relationships between variables, which is what a chi-square test does. So maybe we can use this without getting into too much trouble. Oh, well, it turns out if we do a Spearman correlation, we get, within rounding error, the same p-value. So even though we're told, or lots of sources will tell you, categorical data, chi-square test, Spearman correlation, you get the same result. What about Kendall's tau correlation? So this is similar to Spearman's, what happens there? Oh, same result, p-value 0.122. So it's within rounding error. But I mean, these are, maybe special in some way because, like I said, they're known as non-parametric tests. So they don't have the kind of stringent assumptions that other tests have. So you would believe. So maybe, maybe it's reasonable that you get the same result. And also, the Dalek of statistics has not appeared, so there can't be anything too wrong with doing that, I guess. What about a Pearson correlation? So this is what's known as a parametric test. And when you do parametric tests, you'll have people tell you there are assumptions that have to be met. So for example, the data have to be continuous. Otherwise, So although I'm a bit nervous about doing this, I'm going to have a go with the Pearson correlation, see what happens.
You have disobeyed the laws of statistics. You will be exterminated. Oh. You get the same result. Oh, I might go and have a cup of tea.
Well, that wasn't so bad. We got the same result. Dalek seemed a little cross, but not too bad. What about t-tests? Now, t-tests, they're supposed to be for comparing two means. We don't have any means, we've just got count data. So this is definitely, this is radical. This is like anarchic even, to even contemplate doing a t-test.
I'm warning you, do not do the t-test.
I mean, but I really want to do the t-test.
You will be exterminated.
But I really want to do the t-test.
Do not do the t-test!
Screw it, I'm going to do the t-test.
Ah!
Oh, what would you know? You get basically the same result in terms of the p-value. Okay, I'm going to push this a bit further. A one-way ANOVA. Now this is a test that you're supposed to apply when you have three means. We don't have any means, let alone three of them. So this should definitely mess up the whole fabric of the universe.
You are insane!
It turns out you get basically the same p-value. What about a linear model? So this is the thing we're going to be talking about, regression. You get the same p-value. Log linear model, don't even really know what that is, but it gives you the same p-value. What about a multi-level model?
Now you're pushing me too far. I am going to explode the universe if you do this.
I'm going to do it.
Don't do it.
I'm going to do it.
Don't do it.
You get the same p-value. Well, this is weird, isn't it? Because if you look at lots of resources, it tells you there's certain tests for certain situations, but we've just seen we've done a whole variety of different models and they all basically give us the same p-value, which is the thing that a lot of scientists will focus on. Why is that? I mean, that's just weird. Because you see in certain textbooks, they often have flow diagrams in the back, really complicated flow diagrams that, what's your outcome variable, what type of variable is it, how many predictive variables did you have, what did your dog have for dinner, is it a Tuesday, is it sunny, is it rainy, and then you answer all these questions and it tells you, that's the test that you need to do. But basically, that's all rubbish because most of the time, the only model that you need to fit is some kind of version of the general linear model. You don't need all this stuff, really. You don't need a flowchart. What you need to do is think about the variables in your general linear model. So the only equation you ever actually need is the equation of a straight line or the equation of the general linear model. And if you understand that, essentially everything we do is just going to be a contraction or expansion of that model. So you just need to understand the idea that we're predicting an outcome variable from one or more predictor variables. And those predictor variables can differ in their type. They can be continuous or categorical, but the model itself doesn't really change in essence. So again, you can do a little mental quiz here. Within this model, we've got some betas or parameters attached to the predictor variables. So in general, we could call these beta n's. So the n just, is a number that, whether it's the first, second, or third predictor variable. So do you understand what, have you learned before what that represents? Now, if you've heard of the equation of a straight line, you should know what that represents, or it should be familiar to you, because it's the gradient of the line. But in statistical terms, although that's kind of geometrically what it is, it statistically represents the relationship between a predictor variable and an outcome. So it tells us about the direction and the strength of the effect between two variables, so between the predictor and an outcome. And that can mean, if the predictor is categorical, that it can represent differences between means as well. We also have a parameter, or beta, in there, beta 0, which is not attached to a predictor, and this is known as the intercept. And this just tells us the value of the outcome variable when all of the predictors are 0. So what's the kind of baseline, or baseline's maybe the wrong word, but what's the level of the outcome that you get when all your predictors are 0. So let's have a look at some examples of the linear model. So this is an example that's very close to my own heart, because I like music a lot, I go to concerts a lot. And here's some photos of me and my wife and I at the Download Festival quite a few years ago now, because this was before we had children. And it was very muddy as well, which, may explain why we haven't been back for a while. Go to concerts a lot, and periodically I worry about my hearing, because although now, you can wear earplugs and stuff, I'm sufficiently old that when I was going to concerts as a teenager, the idea of earplugs was, ridiculous or something. You just didn't, you couldn't get them. You probably could get them, I guess, but you didn't wear them. So, I kind of worry that my hearing has taken a bit of a bashing. So we could have a look at what the effect of music volume is on how long your ears ring for. So if you go to a concert, is there a relationship between the volume of that concert and how long your ears ring for? So your outcome variable is how long your ears ring for, and your predictor variable is the volume of the concert. Now, if we had lots and lots of people attending a concert, and we measured, attending lots of different concerts, and we measured the volume of the concert, or maybe it's the volume in different parts of the room, because I guess that will vary a bit. We could have a measure of the predictor, the volume, and we could also maybe ask the people to report back on how long their ears were ringing for after the concert in minutes. And we could plot these. So we've got a load of data points, all representing people. So down here we've got 2 people, and the volume of their concert was, well, I was getting about 92 decibels, and their ears were ringing for, I don't know, like 860 minutes or something like that, or thereabouts. So you could look at everyone's data and then basically estimate the line that kind of best represents that cloud of data. So the linear model that we're fitting is that red line going through the cloud of data. And we've seen there are parameters for this model. So the beta attached to volume is the slope of that line. So it's the rate of change of ears ringing as the volume goes up. So how steep is that line? So if beta's a large positive number, relatively speaking, then what that means is that the duration of ear ringing is going up very rapidly as the volume of the concert increases. Whereas if it was a negative value, that would mean that the amount of time your ears were ringing for was actually going down as the volume of the concert went up, which would be a bit strange, but it could happen. And if the line was completely flat, it would mean that as the volume of the concert increases, it's not affecting how much your ears ring at all. We've also got this beta 0 though, and to have a look at what this means, we've got to kind of scale out of the graph a bit. So we've got our cloud of data and our line here, but if we were to extend this line backwards, right to the point where the volume of the concert was 0, so no noise whatsoever, the question is, how long were people's ears ringing for? And that's what beta 0 represents. It's the value of the outcome when the predictor or predictors are 0. So beta 1 doesn't change. That's still exactly the same, even though we've extended the model. But beta 0 is telling us in this case, it's nowhere near the data cloud, so it's a predicted value, and we maybe need to take it with a pinch of salt. It's saying if you have no volume whatsoever, how long will your ears ring for? Now, clearly this value should be 0. If you have no noise, your ears shouldn't ring at all. But what we find when we estimate this model is actually the value is 37.12. So that's kind of illustrative of the fact that it's a model with error. So you'd expect the intercept to be 0, you'd expect no ear ringing if you've had no volume, but in actual fact it's predicting that you'd have minus 37 minutes of ear ringing. It also illustrates the fact that the values you get out of these models can be ridiculous. So it makes no sense to have your ears ringing for minus 37 minutes. Like, what does that even mean to anyone? So, always bear in mind when you're fitting models that sometimes the actual values that you get out, the estimates that you get out of the model, they don't have to make sense in the real world. It's always good to interpret them and question them. Okay. We could address the same question a different way. So rather than looking at the volume of the concert, we could just look at attending concerts versus not attending concerts. So here we might have two groups of people, a group that don't attend the concert or concerts, and a group that do attend concerts. And look at, again, how many minutes their ears ring for. And so basically you get two clouds of data, it's two different groups. And the linear model here is representing the differences between the means of the two groups. So you can see the blue cloud, or the cloud on the right of the screen, is those that attended the concert, and that they have a higher mean. So the mean of that group is higher than the mean of those that did not attend the concert. And the difference between those two means is what beta 1 is going to represent. And beta 0, the intercept here, it represents the mean in the what's known as the reference category. We're going to cover this in a few weeks, so it'll make more sense. But just bear in mind that in this case, the intercept is a mean of one of the groups. When we fit statistical models, we're trying to make general conclusions. To take our hearing loss example, we would want to make conclusions about how volume at concerts affects everyone, not just the people at a particular concert. So in an ideal world, we'd be able to collect data from everyone ever going to a concert, and the full range of volumes that they might experience, measure their hearing loss, and fit that model, or fit a model to all the people that we want to draw conclusions about. But life isn't like that. We don't have access to everyone that we want to draw conclusions about. And so instead, we typically work with samples. So we would take a smaller set of people and hope that they are representative of the wider population, and we fit our models to that smaller sample. Now, there'll be more on this in due course. The analogy I always draw with this is architects. So if you're an architect and someone says to you, build me a bridge across a river, what you don't do is order yourself a load of concrete, iron rods, suspension cables, blue tack, what else would they use to build a bridge? Duct tape. Bound to use duct tape. You wouldn't go and order a load of that and build yourself the bridge. Like, hey guys, I've ordered all the stuff, I'm going to build me a bridge over the river. Let's go. What you'd want to do first is some tests. So you would build a scaled down version of your model. I mean, probably a lot of it's done with computers these days, I guess. And then you'd put that model to some tests and see how it performs, and if it performs well, if it's like a good fit of reality, then you might actually build the full-scale bridge, or you might generalize your conclusions to a bigger scale model. So you might, for example, say, well, on this river, the bridge is going to be subjected to some rain. So let's see how it holds up, how our model holds up to some rain, and you subject it to a rainstorm. And if it survives, happy days. You can assume that your bridge will survive. So you'll make certain assumptions about the bridge's tolerance to rain. Then you might say, well, it's going to be subjected to some wind. So you put it in a wind tunnel or something and see how your model performs when it's subjected to wind. And basically, you'll have a certain set of assumptions about your model. So it will survive winds up to a certain tolerance and rain up to a certain tolerance. And as long as those kind of conditions are met, then it's fair to assume that your full-scale model will also perform well. There may be things in the world that cause your model to not perform very well. So one thing architects will always kind of overlook when they're building bridges is the threat of the pink river hippo. Now, the pink river hippo has 3 defining characteristics. First is that it's pink. The second is that it lives in a river. And the third is that it has really deep-seated rage against humanity, bottled up over generations of pink river hippos. And this rage can be unleashed at any time. Now, the problem is, for the pink river hippo, the pink river hippo thinks that all the other hippos get too much attention in wildlife documentaries. And this makes it very sad and very angry. And that anger sometimes comes out, maybe it's been watching the Discovery Channel and there's been a hippo documentary and it hasn't been featured. That rage comes bubbling up to the surface and it will strike. Now, the problem is, for a bridge builder, is you might think, well, I'm building over a river where there are no pink river hippos. But what if a pink river hippo gets loose and goes down that river? Then you may find your bridge destroyed. So your model's only as good as the assumptions that you make, or it's only good to the extent that the assumptions that you make are true. So if you make the assumption it won't be attacked by a pink river hippo, and that in fact is the case in the real world, then your model will hold up pretty good. However, if you make that assumption and it turns out that your actual bridge that you build is in fact falls foul of the pink river hippo, then clearly your model wasn't very good. Anyway, what's this got to do with statistics? I've got no idea, but it does at least demonstrate to you why I didn't go into a career as a filmmaker. So to take our ear-ringing example, if you imagine that this is the population model up here, what we are doing effectively is taking a sample. So we're taking a small subsection of that population and we're fitting the model to it. And the model, hopefully, will be pretty similar, but it's not going to be exactly the same. So the parameters, the B's that we get in our sample, are not necessarily going to be exactly the same as the B's in the population. Of course, we don't know how similar or different they are because we don't have access to the ones in the population, but we always have to try to kind of have some kind of estimate of our uncertainty in those values. That's very important. So for example, in this sample, it's telling us that beta 0 is 18.06 when in the population it's 5.5, so they're quite different values. But we could look at taking, imagine we took some other samples. Again, we're getting slightly different values of beta 0 in all of these. And we're also, so the actual kind of relationship between, so the beta for the volume of the concert and ears ringing is about 10 in the population, which of course we don't know and we have no way of knowing. It's like a mythical unicorn value that, we can't, it's probably not as pretty as a unicorn, but we have no access to it. In our sample, we're getting values close to 10, like 9.94, 10.1, 9.76, 9.48. So if we took lots and lots of samples, we'd hopefully get values for beta that are close to the population, but the point is they're going to be different across different samples. There's what's known as sampling variation. There's variability in the estimates you get from different samples. So we're going to come back to this in a bit more detail in another lecture, but worth flagging here. So how do we estimate these values? Well, we're going to use a really, we're going to kind of get everything down to sort of the most basic model that we can think of to use as an example. So typically, I mean, there are other estimation methods that we don't cover on this module. All the models we cover on this module use something called ordinary least squares estimation. So we'll have a look at an example of this using the most basic model that we could use. And that is the mean. So we can use the mean as a predicted value. It's not necessarily a great model to use, but it's a model we can use. So the example we're going to have is the number of friends that statistics lecturers have. So imagine we got a sample of 5 statistics lecturers, and we just measured how many friends they have. So the first one had 1 friend, that was his hand. Second one had 3 friends, third one had 4 friends, next one had 3 friends, next one had 2 friends. So they're our data. And someone comes up to us at a party and says, you know, how many friends do you think I have? And, you know, we happen to know they're a statistics lecturer. So we could use the mean, if we knew the mean of the mean number of friends that statistics lecturers have, we could use that as a predicted value, so, or a sort of best guess. You know, it's a great party trick. I mean, if you're ever at a party, just try this. It's like, you'll have so many friends by the end of the evening. It'll be unbelievable. Oh my God. So we could use the mean, but how do we find out what the mean is? How do we find out what the value of the mean is? Well, it turns out the mean is an example of least squares estimation. But to begin with, let's imagine that there's no maths. Now you might say, how can we possibly imagine that? Well, so before we get into this, I want to introduce you to Professor Hippo.
Hello.
I have to try and move off camera because I can't actually not move my lips. Now, Professor Hippo, he is a genius.
Thank you very much.
And you know, it's kind of I'm just kind of like the you know, puppet. I'm Professor Hippo's puppet. I deliver everything. He's the brains behind the outfit.
Yep.
And he's also all powerful. You know, we've learned before about the power of the pink hippo, right? And he's also quite cranky.
Yep.
And one day he decided to remove maths from the universe.
Yeah, I don't like maths. Sucks.
So he decided to remove all maths from the universe. And but we needed to find out a mean. But we couldn't use maths. So what we could do is guess.
Yep, have a guess.
So let's imagine we're trying to guess what the best predicted value of the number of friends of statistics lecturers is. Now what we could do is we could have a guess. Our first guess is going to be 2. We think on average 2 seems like a good amount of friends for a statistics lecturer to have. Now what we can do is we can rearrange this little equation which says predict friends from the mean, that's what that parameter is going to be, the mean, plus some error in prediction. So we predict the number of friends for a particular lecturer, I, from the mean, and there'll be some error. And if we rearrange that, so we basically take beta 0 over to that side, and it gets a minus symbol when it goes over, we can see that we can work out the error by looking at the number of friends minus our estimate of the mean. So our estimate of the mean is 2. So we've got this lovely table here. So we know the actual number of friends in our sample, we've got an estimate of 2, and this is represented graphically over here. So the flat line is our kind of best guess of 2, and the dots are the actual values. So what we can do is we can work out the errors in prediction. So the errors in prediction are the differences between what the line predicts and what we predict. What the line predicts and the actual value that was observed. So for example, for this first person, they had 1 friend, we predicted they had 2 friends, so we actually over predicted. So we get a -1 as the error, because our model over predicts how many friends that they had. And we could do that for everyone. So the second person, they had 2 friends, we predicted 2 friends, so that's an error of 0. The third one had 3 friends, we predicted 2, so they actually had an error of +1, so 1 more friend than we predicted. We could do that for all of them. And we could add all of these errors to work out what the total amount of error is. However, notice that some of them are negative and some of them are positive. And if you add positive and negative numbers, they're going to cancel out. So we can't just add them up. We have to do something to get rid of the negative numbers. And one of the things we can do, it's not the only thing, but one of the things is we can square them. If you square -1, it becomes 1. So what we actually do is we look at the squared error. So we take these errors and we square them. So -1 times -1 gives us 1, 0 squared is 0, 1 squared is 1, so on and so forth. And it's these squared errors that we add up to give us a total amount of error in our model. So when we use a parameter of 2, the total error in prediction is 7. Okay, doesn't seem too bad, but can we do better?
Yep. Have a guess of 4.
Okay, have a guess at 4. So let's have a guess at 4 then. So when we guess that the parameter is 4, when we guess that the mean is 4, our estimate's now changed to 4. Our model is this flat line, which is now at 4 instead of 2. And again, we can look at the errors by looking at these distances between what was predicted and what was observed. So, let's just have a look at those. So for our first person, we get an error of -3, second one, error of -2, -1, -1, 0. Again, we could square these values so that we can add them up. And what we find when we do that is we end up with a total error of 15. So this is bigger than the error we had before. So this tells us that our estimate of 4 is worse than, it results in more error in prediction than our estimate of 2. Now, if we were particularly sad, what we could do is try out every possible guess of beta. So we've tried 2, we've tried 4, or we could try 3, we could try 5, we could try 2.1, we could try 2.5, we could try everything. And if we did that, what we would see is this. So this is a curve being drawn of every estimate of beta going from 0 up to 5, and on the y-axis it's telling us the sum of squared error. And as you can see, it has a characteristic curve. So it basically curves down, reaches a minimum value, and then the error starts to come up again. So there is a value. There is a value of the mean that is the minimum possible value given the data. So here's that curve. And here are the 2 values that we guessed. So there's that we guessed a value of 2, and that gave us an error, total error, sum of squared error of 7. We tried a value of 4, that gave us a total sum of squared error of 15. So those are the values. The question is, what is the value right down the bottom? And the value turns out to be 2.6. So this is the value of the mean or the value of the parameter that gives us the least squared error, the least sum of squared error. So this is an example of ordinary least squares estimation. So if we plug that number of 2.6 in as our estimate, here, and we work out those errors, so we get an error of -1.6, -0.6. I don't know why I've still got a hippo on my hand. 0.4, 0.4 and 1.4. And we work out those errors and we square them, we get this value, 5.2. So that's the least squared error that there can be given the data. Now, that was a very long-winded way of doing that, but I'm trying to illustrate what least squares actually means. Now, there's actually an equation that represents this least squared estimate. This equation you might be familiar with. So it's, you just add up the scores. That's what this top half is doing, and then divide by the number of scores. It's the standard equation for the mean. And this equation actually gives us the least squared estimate. So the mean is a least squared estimate. So we add up the scores, 13, divide by the number of scores, 5, we end up with this value of 2.6, which was that lowest point of the curve. So the equations that we use, so as we fit more complicated models, the equations get more complicated and we don't need to know them or get involved with them, and indeed we don't. But essentially they're doing the same process as this. They're fitting mathematical equations that will give values of the betas that have the least squared error in much the same way as the mean. An important point here is the mean that we get here is 2.6. That's not a value that actually occurs in the data. So that mean, or that value of the parameter, always has error. There is no one in the data set that actually had a score of 2.6. So for every person in the data set, the predicted value of 2.6 is incorrect. There's error associated with it. And that's an important thing to bear in mind. There's always uncertainty. Because no one would have 2.6 friends.
I've got 2.6 friends.
No, you haven't.
Yeah, I actually have.
No, you haven't.
I have.
How have you got 2.6 friends?
Well, I have 3 friends, but I didn't really like the top half of one, so I cut him in half and put the top half in the fridge. I just like his legs.
So you had a friend, you've now got the legs of a friend, the rest of the friends in the fridge.
Yep, that's right.
Okay. Why?
Because I'm a psychopath.
Ah! Get off! Get off! Get off me! Get off! Ah!